Hi, everyone. Have any of you built agents? Yes. Oh, good. Do you just wish your agent could keep running and never fail, no matter how many people are hitting it, no matter what random request your users are throwing at it? Yes. Great. That's what we're going to talk about today. We're going to talk about how to make our GenAI agent resilient. My name's Yiwen Zhang. I'm a GenAI specialist, principal architect here.
And I'm Jennifer Moran. I am a Senior Resilience Specialist SA here.
OK. Here's our agenda. We're going to spend a little time to clarify what is a GenAI agent. And then we're going to break it apart, see what are the components and layers inside of the GenAI agent that could cause resilience problems. And then we're going to talk about different resilience controls and end with operational excellence. So what is a GenAI agent? The official definition says it's an artificial intelligence agent that is a software program that can interact with the environment, collect data, and use the data to perform self-determined tasks to meet the goals. It's very dry and doesn't say a lot of things. Let's break it down. So there are 4 things. One is you need to have a reasoning engine. The agents are goal-oriented. So it will achieve the goal, although the path is not predetermined. So you use the reasoning engine, such as React, chain of thought, to break out how do we achieve that goal. Second, it has memories. It cannot just be a one-off question answering. You need to have a short-term memory to know what's the conversation context. You can also configure a long-term memory to have the basic user information there to give the agent more context to complete the task. And you need to have the planning capability. So the goal could be a really big ask. Then the agents need to be able to break it down into smaller, chewable sizes, different steps, and need to order these steps in the right order to achieve the goal. And the last, you need to use tools. Without the tools, the agents are just a chatting companion. With the tool, it can get things done, right? And it can use these external APIs or databases for help. So that's the characteristics of agents. Now, pop quiz. Is Llama 3.3 an agent? Good. I see a lot of shake heads. That's no, it's just the language model, right? What about Claude? Is Claude the app an agent? No. Oh, some of you say no, some of you say yes. I could argue that with the right configuration, it could be an agent. It has the reasoning capability. You can do the planning. It has the memory for sure. And right now, it has different tools you can configure it. So if it's configured right, then it could be an agent. OK. So there. And the agent to the user is a cute chatbot. And we can throw in some tasks. But for the developers, we know there are a lot of things behind the scene. Let's break them apart. We put the agents into these 7 layers. I know it's a lot. We try to consolidate it. But these 7 layers are platform agnostic, agent development framework agnostic. So whatever way you build agent, you can always map to these 7 layers and then analyze whether they're resilient or not. OK, the first layer is the foundation models. That's where everything started. We have large language models. They provide the reasoning capability. They provide the planning capabilities. And then on top of that, we start to build the agent orchestration. These are the logic we built into the agent. They determine what are the sub-agent to call, what are the tools we can use. OK. And then now we have agent, the software layer. There's also knowledge base. So we pull knowledge base out as a separate layer because there are 2 components in the knowledge base. One is the storage of this vector database. And the other part is the embedding model that help us ingest and build knowledge database and handle the queries. So we need to consider both the storage resilience and the embedding model resilience. Next is the agent ecosystems. So this includes all the tools the agent can call, these external APIs. It also includes other features such as prompt caching, prompt management. The next one is the deployment infrastructure. With all these different components we can deploy. So where do we deploy these agents? We can use the old-fashioned way. I got a bunch of Linux server. I can got some EC2 instance. I just manage it my own, and I deploy my agents there. You can also choose to use managed service, such as Bedrock agents. In this case, Amazon Bedrock is responsible to keep your agent up and running, while the development team need to control the agent's logic and how it's built. The sixth layer is security and compliance. The security side include the security of the agent, so who have access to the agent. Quite a lot of cases, we need to consider a more granular access control. So certain users can only have access to certain tools. Certain users can only have access to a certain part of the database. It also includes the agent's safety and security. So when the agent is operating, especially when you give it certain tools, it will have a lot of power. So how do we control the agent only operate on the resource, on the task that we want them to operate on? And also the compliance side. We need to control the users only asking for questions and within the agent's response scope. Oh, the last layer is most important. Because of the complexity goes into the agent, we need to have really good observability to keep track of what is happening at every step. And to build high-quality agents, we need evaluation at every step. So the answer is final one answer. But we need to evaluate which step that is making them most easy to break, and then we can improve on that. So those are the 7 layers. And then let's talk about the resilience controls over them.
Okay, so now we're going to talk about the resilience controls. So I have a question for the audience. Has anyone heard of the resilience analysis framework? Oh, nobody. All right, this is fantastic, because that's what we're going to talk about over the next couple of slides. So let me tell you a little bit about it. So the idea is that the resilience analysis framework came about by the resilience teams at AWS working with our customers. And the idea is that all resilient workloads, no matter what they are, will have 5 key resilience properties. Those properties will have corresponding failure modes that will try to contradict that property. And the idea is by having these properties and these failure modes, you can do a resilience modeling exercise where you can try to identify the failure modes that are trying to challenge that property and be able to put resilience controls in place to either prevent, detect, or mitigate against those failure modes. So that's what we're going to talk about today. So I want to draw your attention to the screen where, as you can see, we have the 7 layers that Ewan just explained. And we're going to walk through the different key resilience properties, the failure modes, as they relate to the ones that are green. Now, that's not to say that you wouldn't want to look at these resilience properties through all of these layers, but we only have 20 minutes. So we're going to try to highlight some of them using the different 7 layers. So the first one is fault isolation and shared fate. So fault isolation is being able to build boundaries in order to prevent a cascading failure. And the idea of shared fate is that sometimes within those boundaries there are, or crossing those boundaries, are common dependencies. And the reason that it's a shared fate failure mode is a lot of times you don't know that there's a dependency between those layers or across those boundaries. So if we think about this from a GenAI workload, we can think about from the reasoning layer putting in either physical or logical boundaries, right? So think about your foundation model that is providing a hallucinated output, and you don't want to have that cascade to your next layer, right? You want to be able to contain that output through validation processes and not have it call the next layer or the tool execution because the output is not good. We can also think of a circuit breaker pattern, which is also something that we can implement in our orchestration layer, where we know, or we can put in this pattern to understand if one of our tool executions is being overwhelmed, right? It's not responsive, there's too many calls going to it, it's not able to handle that request. So what we can do is, instead of calling that when we know it's going to fail, we can put a circuit breaker in there and trip the circuit, meaning don't call that tool execution until it's able to respond and come back from being overwhelmed. We also want to think about distributed tracing. So you see all these layers, right? And we want to make sure that we have that distributed tracing across each of these layers. Because what's going to happen is we want to make sure that we understand what's happening both at the layer and between the layers. And we want to see if there are unintended boundaries getting crossed, right? So again, things that you may not think are a dependency between the layers, but actually are. So our next property is redundancy. And this can be redundant components, this can be redundant paths. And the idea is that this is going to eliminate single points of failure. If you have a single point of failure and that component or path fails, you could potentially have a system-wide outage. So we want to put redundancy in place to mitigate that. And the way that we can do that from the foundation model perspective is, if you are using Amazon Bedrock does have a multi-region model deployment. So it does offer in some models a cross-region inference where the redundancy is handled by the service for you. So it's going to take care of, if one path is not available for whatever reason, it's going to choose that alternate path for you. We can also talk about automated failover process and alternate tool routing. So we talked about circuit breaker last time in the previous slide. This kind of goes hand in hand with that, right? We want to know that if the circuit breaker is tripping, we have an automated failover process that can use an alternate tool. That's still going to provide the same characteristics of that original tool, but again, you have that alternate routing, that redundant path that you can use. We also want to make sure that we have replication lag monitoring for our knowledge bases. So having a replication lag between your primary and your secondary knowledge base is going to be important. And you want to make sure that you have SLAs identified for that replication. And you want to be able to understand if you are breaching those SLAs, because you want that knowledge base, whether it's the primary or the secondary, to be accessible to the tools that needs it. And finally, monitoring all paths. Right? So if you can monitor both the different components, redundant components, and the different paths, you're going to be able to identify when there could be a potential issue happening, right? So you can get a leading indicator to say, oh, there might be an issue with this. Let me go and see, make sure that I can take care of it before your users have a bad experience. Third is going to be sufficient capacity and excessive load. So sufficient capacity is when our workload is able to handle regular traffic and unexpected surges. But excessive load can actually compromise even the most well-provisioned systems. So what we want to do with excessive load is we want to make sure that we are managing our quota management, right? And we want to do this in an automated fashion. So we want to make sure that we understand our token quotas, because what we don't want to happen is we don't want a single complex conversation exhausting all the resources for all of the other users. So we need to make sure that we are on top of that token quota. Also, intelligent request throttling. So what we can do is we want to use priority resource-based allocation. And we want to make sure that the most important calls or requests are the ones that get through. And what we can do during peak load is the ones that are less critical can sort of take a back seat to the ones that really matter. Reducing search depth. So in our knowledge base, having high peak at times, you can reduce that search depth, right? So making sure that you're still having those critical conversations can come back from that knowledge base. But again, just reducing that search depth so you can manage that load. And real-time capacity monitoring, right? Making sure that, again, we're actively monitoring those tokens, we're actively monitoring model inference times in order to be able to proactively scale when we need to. Again, because what we don't want to happen is our users to have a bad experience. And then I'm going to pass it back to Yuen, and she's going to do the next two.
Thank you. Okay. Timely output. Who has a user that expects your GenAI agent can produce an answer like that immediately? Right? They all do. Well, this is a typical trade-off between cost, quality, and latency. I've never met any user who will say, I will give up on quality. Just give me answer fast, right? Because quality is always the first priority. Right now, we're still at the stage to win the trust from humans. So given that they expect high quality, then the agent needs time to think. So given these constraints, how can we make the agent have lower latency? Well, the first thing to do is define the service level objectives, just old-fashioned expectation management. Have the conversation with the user up front. Do you have to have the answer immediately, or can you wait for like 5 minutes? Quite a lot of cases, some old tasks will take hours or many days for a human to complete. Now it's going to take 10 minutes for an agent. If the conversation happens up front, it's probably okay. Otherwise, they're going to sit staring at a spinning wheel for 10 minutes. It's a really bad experience. And the next one is optimize agent orchestration. So when we build the agent, because of the non-deterministic nature of these GenAI applications, it's going to go through a lot of different iterations. It's going to do its own planning. It's going to think through steps and then ruminate on its steps and think about whether I made the right decision. So if we can optimize that, analyze what the agent has think through. Is it because of some of the instruction I give to the agent, make it take certain actions? That could largely reduce the time it spent on ruminating these steps. Next is the latency observability. Of course, have transparency over what's taking time at every step. It could be the reasoning steps. It might be the tools just taking a long time to do what it needs to do. Also, if all of these has tried, then it still need to take time and the user expect results immediately, we can start to stream out the answers instead of having to finish generating all the text and then send a big blob. And there's also some of the agent development framework provide async processing capabilities. So you can trigger the tools asynchronously when they're not interdependent. You can also trigger multiple sub-agents asynchronously, so it saves some time. And the next property is correct output. And this we're not talking about the overall accuracy of the large language model accuracy. This we're talking about when we build an agent and we define this as a scope, we need to make sure that it answers within this scope. So the first thing to do is to validate the input and the output. So is the user's ask within my agent's ability to answer it? If not, let's stop it right there. Also, we can leverage deterministic agent flows. So when we have the agent, it can do a lot of different things. We can rely on all the non-deterministic nature. But if we know certain tasks need to be taken or certain sub-agents could be triggered when user says certain things, we could build the rules into the agents. And that way, it takes out the non-deterministic nature of the agent and largely enhance the accuracy. And performance evaluation is so important. Because of the different steps the agent needs to take, we need to have a transparency on what it's doing every step and evaluate it at every level when we want to improve the accuracy. Is it the reasoning engine doing the right job up front? Did it create the right plan to execute my task? If it's the right plan, is it picking out the right tools or the right sub-agent to do the task? If it's the right tool, did it pick out the right parameters for these tools to feed in to execute on the queries? If the tool is doing the right job, did it return it back to the agent? And did the agent use that information to generate your final answer? So have that transparency over these steps is super helpful. And last one is when the certain task is at high stake, we can introduce human in the loop. So if you're using Bedrock agent, there's the confirmation step you can introduce. It's within the agent. Human can confirm before it can carry out certain tasks. If you're using some open source framework, you can pull out to a human node. And then there you can define what action to take when human approve or disapprove certain actions. Okay.
Okay. So finishing up, operational excellence as it relates to generative AI. So really the idea here is take your traditional DevOps practices and think about how you would incorporate AI-specific things through their lens. So for example, thinking about strong engineering teams that have model management capabilities, using ML ops. Again, we talked about observability, adding in those AI-specific metrics. So all of this is going to be important, and again, it's your traditional DevOps practices, but just sort of tweaking to add those AI-specific elements. So we covered a lot, and our key takeaways for you are we challenge you to go back and take your workloads, use the 7 layers that we identified, map your workload to those layers, do the resilience modeling exercise with the 5 key resilience properties and failure modes, and think about your operational excellence and how you can put an AI lens on it. So that's it. If you have any questions, we're actually going to be on the side of the stage for you. So thank you very much.